The red dirt of far north Queensland doesn't look like much. Flat, quiet, almost featureless. No towering mountains, no dramatic cliffs, nothing that signals importance. Just a low, dusty plateau stretching toward the Gulf of Carpentaria. But beneath that surface sits one of the most essential resources on Earth, a material that quietly supports the modern world, yet almost no one has ever heard of it. Every year this place produces tens of millions of tons of ore. It generates billions of dollars in value. It feeds the global aluminium industry, which underpins everything from aircraft and smartphones to power grids and construction. And yet, despite its scale, despite its economic weight, it remains largely invisible. Because this isn't a gold rush story, it isn't iron ore hauled from towering pits, it's something far stranger. This is the Weipa bauxite deposit, one of the largest accumulations of aluminium ore on the planet. And unlike most mineral deposits, this one isn't simply ancient. It hasn't just sat here unchanged for millions of years. It's still forming right now. To understand why that matters, you have to let go of what a mineral deposit is supposed to look like. This isn't a solid body of rock. There are no veins to follow, no massive ore zones cutting through the ground. Instead, the entire deposit is loose, fragmented, almost granular. If you were to pick it up, it wouldn't feel like rock at all. It would feel like gravel or coarse sand. That's because the deposit is made up of countless tiny rounded grains known as pisoliths, each one only a few millimeters across, typically around 3 to 5 millimeters in size. Small enough to overlook, but inside each of those grains is aluminium-rich mineral matter, primarily gibbsite and baumite, the raw ingredients for aluminium production. And that's the first hint that this system is fundamentally different, because most bauxite deposits form in place. They develop directly from the rock beneath them, preserving the structure of their original source. You start with something like feldspar-rich material. Intense weathering strips away silica, and aluminium is left behind as a residual concentration. But Weipa doesn't preserve anything. It has been broken apart, reworked, rounded, sorted, and rebuilt. What exists here today is not just the product of weathering, it's the product of movement. The story begins more than 100 million years ago, when this part of Australia was still covered by a shallow inland sea. As that sea retreated, it exposed vast stretches of flat-lying sediment across western Cape York. Sandstones, clays, and marine deposits were left behind, forming the foundation of what would become the Weipa Plateau. From that moment onward, the conditions were ideal. A warm climate, high rainfall, a relatively flat landscape. Exactly the combination needed to drive one of the most powerful geological processes on Earth, lateritic weathering. Over millions of years, rainwater began to infiltrate the exposed rocks. Silica, one of the most mobile components, was gradually dissolved and carried away. Aluminium, far less soluble under these conditions, remained behind. Slowly, the chemistry of the ground began to change. What started as ordinary sediment was transformed into a deep, aluminium-rich weathering profile. At first, this would have looked like a typical laterite, clay-rich, iron-stained, gradually enriching upward in aluminium. But then something critical changed. The system didn't stabilize. As weathering intensified, the structure of the material began to weaken. The clays that once held the profile together started to dissolve. The ground became softer, more porous, and more fragmented. Instead of behaving like a cohesive mass, it began to behave like a collection of particles. And once material reaches that state, it becomes mobile. Rainfall alone is enough. Seasonal wet-dry cycles, sheet wash across the surface, slow downslope movement, all of it begins to redistribute the material. Not in dramatic landslides, but in subtle continuous shifts, grain by grain. As those particles move, they begin to change. Each fragment becomes a nucleus, a starting point. As it sits in aluminium-rich fluids, the thin layer begins to form around it. Then it's disturbed again, rolled, broken, and moved. Another layer forms, then another. Over time, these particles grow into pisoliths, small rounded grains with layered internal structures, like miniature geological onions. Each layer represents a phase of growth, followed by erosion, followed by regrowth. Some have cores made from broken fragments of earlier grains. Others contain compacted clay or fine sediments. Many show signs of repeated breakage and rebuilding. They are not simple particles, they are records of movement. As this process continues, something remarkable begins to emerge. The landscape starts sorting itself. Heavier, larger pisoliths settle closer to their source. Finer material is carried further away. Over time, this repeated movement creates a broad, uniform blanket of bauxite across the plateau. Not a localized deposit, but a continuous sheet, shaped by the flow of water and a slow redistribution of material. This is why the Weipa deposit is so extensive. It isn't confined to a single structure or host rock. It spreads across the landscape, following subtle changes in elevation and drainage. In low-lying areas, the bauxite thickens. On higher ground, it thins or disappears entirely. It behaves less like a rock formation and more like a sedimentary system. And like any sedimentary system, it never truly stops evolving. Even today, the edges of the plateau are being eroded. Pisoliths are being washed downslope and redeposited in lower areas. New material is constantly being added from above. Dust, clay, organic matter, termites in particular play a surprising role, bringing fine material up to the surface, which is then redistributed back down through the profile. At the same time, chemical processes continue below the surface. Aluminium-rich fluids move through the ground, depositing new layers onto existing grains. Some pisoliths grow larger, others break apart and become the cause of new ones. Even bushfires leave their mark. Heat alters the mineralogy of the upper layers, transforming gibbsite into baumite, making some grains harder and more resistant to erosion. These more durable grains are then preferentially preserved as the system continues to rework itself. The result is a deposit that is constantly recycling its own material, breaking down, building up, moving and reforming. It is not static, it is active. What makes this even more extraordinary is how consistent the system has become. Despite millions of years of reworking, the pisoliths at Weipa are remarkably uniform in size. Most fall within a very narrow range, centered around just a few millimeters. That kind of consistency doesn't happen by chance. It's the result of continuous sorting, where particles are moved again and again until only a specific size range dominates. It's the same principle that creates uniform sand on a beach or evenly sized gravel in a riverbed. But here, it operates across an entire plateau, over immense spans of time. The landscape itself has become a sorting mechanism, and the product is one of the most uniform bauxite deposits on Earth. Then there's the scale. The Weipa operation produces on the order of 30 million tonnes of bauxite per year. That alone places it among the largest bauxite producers globally. The value of that output runs into billions of dollars annually, supporting not just mining operations, but refining, smelting, and manufacturing industries around the world. But the real importance lies beyond the mine itself. Aluminium is one of the most widely used metals on the planet. It's lightweight, corrosion resistant, and highly conductive. It forms the backbone of modern infrastructure, from transport and construction to energy transmission and packaging. And every tonne of aluminium begins with bauxite, which means this quiet plateau in northern Australia is directly connected to systems and technologies used across the entire globe. Invisible, but essential. And yet, despite its scale, despite its value, and despite its global importance, the Weipa deposit challenges one of the most basic assumptions about geology, that mineral deposits are fixed in time. We tend to think of them as relics, products of ancient processes that no longer operate. But Weipa doesn't fit that model. It isn't a frozen snapshot of the past. It's a living system, still responding to climate, erosion, biology, and chemistry. Some of the material within the deposit may date back tens of millions of years. Other parts may be far younger, formed through more recent cycles of weathering and reworking. Even now, new layers are being added to individual grains as fluids move through the ground. In the same place, at the same time, you have material that spans an enormous range of ages. Ancient cores wrapped in younger layers, old material reshaped by modern processes. A deposit that is both deeply geological and actively evolving. And that is what makes Weipa so remarkable. Because what appears, at first glance, to be nothing more than a flat stretch of red dirt is actually the surface expression of a system that has been running for over 100 million years. A system that has built, destroyed, and rebuilt itself countless times. A system that continues to operate today, quietly reshaping one of the most important resources on Earth. Not through explosive forces or dramatic events, but through slow, persistent change. Grain by grain, layer by layer. Until an entire industry depends on it, and almost no one ever notices. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.